So from the last lecture we saw that suppose you have a B is a algebra, so that means you have a homomorphism F from A to B. Then I say that B is integral over A if B is integral over the subring Fa. This is the notation. Okay. So now it is transitive in the sense that I will leave it as exercise. This is a corollary. It's an important corollary. What it says that if you have suppose A is a subring of B, B is a subring of C, and suppose B over A is integral and C over B integral, then C over A is integral. So hint is that you take an element in C, you try to prove that Ax is finitely generated A module. It's not difficult, you can show it. I leave it as exercise. Another corollary. So let's say this is corollary 1, corollary 2. So let A is a subring of B and C is the integral closure of A in B. So I write integral closure of A in B. So you saw that this is a subring of B, right, in the last lecture. Then C is integrally closed. So what does it mean? That means that if I take an element in B such that x is integral over C, then x actually belongs to C. So this is what it means, integrally closed, right? So again, I leave it as exercise. These are two, elementary exercise, I leave it for you. Okay. But both are very important. Elementary, but these are very useful. Okay. So now so there are two things. Suppose if you have a integral extension, suppose A is a subring of B and B is integral over A. Now you can ask two questions. That suppose I take a ideal in B and take the contraction. So that will say that suppose let and Q be a prime ideal here in B and let P is a Q contraction, so which is in spec of A. So we can talk about A mod P and B mod Q, and you can see that this is also a subring of this. B mod Q is A mod P is a subring of B mod Q. Now if B over A is integral, So, the proposition is the first part of the proposition, say 1, says that if I don't need prime idea actually, for any ideal I can do. Okay, so I'll just I don't need prime ideal. So okay, let me write the proposition. So if B is any ideal in B, it's any ideal, and A is your B contraction. And assume that this is integral. B over A is integral. So, this is assumption. Assume B is integral over A. Then you have A mod A, which is a subring of B mod B contraction integral. That means when you go by quotient, integrality does not change. B is integral over A. Sorry. Huh? Okay. So, this is so another thing is, this is when you take quotient, if B is integral over A, it remains when you do by quotient properly, then it remains integral. Another question you can ask, what about localization? So, that is also true. So suppose, but there you have to take a prime ideal. So, suppose
How can it be proven that A by small a is contained in B by small b?
because A is B contraction, A intersection, A is A intersection B. A is contained in B, right?
Is contained in B.
So, 2 is that suppose P is a prime ideal in A, then consider S to be A minus P, multiplicatively closed set, right. Now, you can talk about S inverse of A, which is nothing but localization at P, and also S inverse of B, though P is not a prime ideal in B, but the set S is a multiplicatively closed set. So, you can talk about S inverse of B, right, S, because S is a multiplicatively closed set and A is a subring of B. So, you can talk about S inverse B. So, I denote it by BP. Okay. So, now the point is that, so the statement is that if B is integral over A, then BP is integral over A. Okay. Proof. So, first is that sub A, so you take an element here in X bar, in B mod B, right. So this gives you element x in B, but B is integral over A. So you have equation, you have a monic polynomial x to the power n a1 x to the power n minus 1 dot 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 a n equal to 0 with ai belongs to A. Now if you go modulo B mod B, then this will say that this the x bar satisfies x bar a1 bar x, where ai bar is in A mod A. Well, so it's quite straightforward. So this implies x bar is integral over A mod A. And the localization proof is also similar. So suppose you take element x mod S in S inverse B, where x is in B, S is in S. So you know x is integral, B is integral of over A. So that will say that x to the power n A1 x to the power n minus 1 dot A n equal to 0, ai belongs to A. Now divide it by s power n, and that will say the x power s, almost similar proof. Now you see this coefficient here a1 by s, a2 by s square dot 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 a n by s power n, these are element of S inverse of A. So this will imply that x by s is the integral over S inverse A. Yeah, that will also work. Yeah, just for yeah, what he is saying is correct. Instead of P, you could have chosen any multiplicative set. So here, it more generally, you could have taken S is any multiplicatively closed set. Correct. But mostly we will do localization. So that is what I wanted to say, that whenever you have a ring, you have two operations. One is quotient, another is localization. When you take quotient ideal, it means that ideals are containing the ideal. I mean the ideal which you are taking quotient, and when you take localization is the opposite. Ideals are which does not. So that's why, I mean, so mostly we will be interested in these two kind of situations. So you are absolutely right. Well, true for when. Okay. Okay. So these are some easy consequences. This implies x by s is integral. Okay. Okay. Now let's. So now I will prove something which is the first step for going up theorem. So this is the proposition. So I write it as proposition 2. So let A is a subring of B, B is integral over A, and further B is a domain. B is B is an integral domain. Then B is an integral domain, and also B is integral over A. Integral domain and plus B is integral over A. Then B is a field if and only if A is a field. Okay. Proof. So, what we need to prove that if you take any non-zero element in B, then it has inverse. So you take any non-zero element in B, so it will satisfy some polynomial x to the power dot a n equal to 0. Now B now first of all, you see, notice here that a n has to be non-zero, because if a n is not 0, then you have some x to the power here, you will have some a n minus 1 x. So which you can write it as x times x to the power n minus 1 dot 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 plus a n minus 1. But it's domain. So domain implies a n has to be non-zero. Once it is non-zero, so I am doing the this part. That means I am proving that if A is a field, then B is a field. So I am assuming yeah. So this you can write it as, if a n is equal to 0, then you can write it as x to the power n minus 1 plus a1 x to the power n minus 2 a n minus 1 equal to 0. But x is a non-zero element, and you assume that n is the smallest integer such that it satisfies this equation. So this is always non-zero. See, integral means that n is the smallest integer, that also you are using. This cannot be 0, because otherwise, because the INQ equation, this is a minimal polynomial which satisfies minimal degree polynomial. So a n has to be so a n is not 0. So if a n is not 0, then you can think x inverse as a n inverse x to the power n minus 1 plus a1 x to the power n minus 2 plus a n minus 1. If you multiply, then what will you get? Probably a minus sign will come, right? Is it clear? Because a n minus a n equal to x time x to the power n minus 1 plus a1 x to the power n minus 2 dot 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 x a n minus 1, right? So, this will, right, you multiply with a n inverse both side minus a n inverse. So, this is a commutative ring. So, if you have a right inverse, it is a left inverse. And so, notation, you multiply with it and you get 1. That is the definition of x inverse.
No, but x we are starting from B. We have to prove it is invertible.
This is the element, right? This is the element. Okay, now converse. So, if you start with the A is a field, then you showed that B is a field. Now, you have to assume that suppose now converse, that suppose B is a field. So, what we have to prove that A is a field. So, let you take a non-zero element in A. So, of course, we know B is a field. So, x inverse belongs to B. Right, and B is integral over A. I want to prove the x inverse also in A. So, you know B is integral over. So, x inverse is integral over x inverse is integral over A. So, so that means they will satisfy some polynomial. So, you can write it as x inverse power m plus a1 time x inverse m minus 1 dot 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 a m x inverse equal to 0. So, if you simplify, what will you get? You will get a m x power m plus a m minus 1 x power m minus 1 dot 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 1 equal to 0. So, now, so this will imply that x inverse equal to minus a1 plus a2x a m x to the power m minus 1. See, note these ei's are in A, and ax you started with in A, and A is a subring of B. So, this element is in A. Okay. So, now as a corollary, so it has a nice corollary. That let A is a subring of B and B is integral over A. Let Q be a prime ideal in B, and P is the contraction, that is P is Q intersection A. Then Q is maximal if and only if P is maximal. That means contraction of maximal ideal is maximal, and it's a both way. If the contraction is maximal, then the ideal is actually maximal. It is not true in general. That was the problem when, that's why we do it spec, but contraction of prime ideal is prime ideal. But when it is integral, it seems that contraction of maximal ideal is maximal, and converse is also true. That if contraction is maximal there, so we will see a direct proof. It's a very one-line proof. So you have a is subring of B, so you take A mod P, which is B mod Q. Now B over A is integral. So now B mod Q is integral over A mod P. Is integral over A mod P. Now if Q is maximal, then B mod Q is a field. So now if you prove, if you assume that if by previous result, that will say that A mod P is a field. So if A mod P is a field means P is maximal. Conversely, if A mod P is a field, that means if P is maximal, then A mod P is a field. So because B mod Q is integral over A mod P, so it will say that B mod Q is field. So that will say Q is maximal. This is a very important consequence. We will see application here. Actually, this is the first step for going up. We will see. Another corollary. Let A is a subring of B. B is integral over A. Let Q, Q prime are two prime ideals in B such that their contractions are same. So that is Q intersection A is same as Q prime intersection A. Let's call it P. Then Q equal to Q prime. So that means if you take two prime ideal in B, if they contract to the same prime ideal, then they have to be same. So how do you, so now you have to use the other one. Localize, integrality does not change if you do localization. So now you see why I wrote that notation, because I will use that. So you take P S to be proof, you take S to be A minus P. So now you have a diagram A, B, A P and B P. Now you take the maximal ideal. So AP is a local ring. So take the maximal ideal M, which is PAP. Right. So be the maximal ideal. In AP. And N is the ideal Q BP and N prime is the ideal BP. Sorry, Q prime BP. So because Q is contained in Q prime, so that will say that N is of course inside N prime. And N contraction is same as N prime contraction, because Q contraction equal to Q prime contraction equal to P, right. Now since AP to BP is integral, and n is what? Q BP, and Q is sub of Q prime, na? Oh, okay, sorry, I made a mistake here. So, Q, so that, and Q is containing in Q prime. That is crucial. Thank you. So, since BP is integral over AP and M is maximal, this implies n, and now you use the previous proposition. This will imply the n and n prime are maximal. So, this will imply that Q equal to, if n equal to n prime, n is Q BP and n prime is Q prime BP, this will say that Q equal to Q prime. Okay.